should be live. In theory. But of course, every time, new season, new bugs. We'll figure this out. People have to confirm our existence. I appreciate the Cthulhu watching over and blessing this this work that we're doing here. Ja, Cthulhu Ftagan. There we go. Some people are telling us that we exist. Yay! Once again, we have been observed, collapsed, Schrodinger's catted. Anyway, how is it possible that you're here, Brian? Is it the future, the time? I don't understand. I guess it's nighttime for you, 8:00, so you're able to make it more this season?
Yeah, I don't have classes.
Did you have classes at nighttime before? I'm trying to remember.
Sometimes I did.
Oh, okay. All right. I was wondering
So the
why.
drive home, I couldn't get there, but
Yeah. Because you showed up promptly as soon as classes were over.
yep, that was kind of the last minute thing. But no, it's my schedule is more flexible now.
That's awesome. Or terrible.
No, it's good.
Yeah.
It's good.
Flexible to be able to go and check out enormous telescopes located halfway around the world.
Yeah, that's always a plus.
All right, so don't forget to say hello. I guess I'll say hello to some people. I'll say hello to my wife. Weekly Space Hangout time. Okay. Hello to Aaron C, Astro B, Adam Scheme Rav, Beth Johnson, Brian Yuku, BTT, David Dunn, David Fairweather, Eric One, George Lancaster, Giselle Sabret, Grant Lanning, Jay Alexanderson, Johnny J, Kevin N, Larry Beckham, Martin Bradshaw, Nancy Graziano, Ocean McIntyre, Paranor, Scott Bragdon, Tom Van Scotter, and Zap Van. Hey, everybody. Welcome to episode 2 of this season of the Weekly Space Hangout with a bunch of new co-hosts who are all very quiet because they're not sure how this all works yet. But that's okay. By this time, 2 months from now, everyone will be really chatty, and we'll be like old friends. So, all right. Well, let's get this thing started then, and do the show. All right. I wonder if we want to do what we did last week and go straight into the interview. No, we won't. We'll introduce all the new co-hosts. All right. Let me get my information. All right, here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, September 18th, 2019. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about the most massive neutron star ever found. Most massive possible neutron star? Saturn's rings, older than we thought. Monitoring air pollution from fires, the new interstellar comet, and maybe more. Joining me this week, let's see, longtime co-host of the show, Dr. Brian Coberline. Brian, welcome back.
Thank you. It's good to be here, everybody.
What's on your blackboard right there?
Things I got to do.
Things you got to do. I see Space Hangout right there. Perfect.
Yeah.
Which is great. I'm glad you can just check that off anytime you want.
That's right. I could actually do that now.
Oh, perfect. Once it's done, once we're successful, how is the TV show going?
The TV show, the sizzle for this. So this is the big science TV show at various science facilities. The sizzle reel is finished and has been sent out to all the supporters. And then the beginning of next month, they send out the pitch to the various networks. So
awesome.
Here's hoping.
All right. So then Michael, you were here last week, right?
Yeah, that was my first week.
Yeah, perfect. So now you're here for your second week. Look at you already. So much more of a veteran. You've got that 1,000-yard stare. You've seen things.
I have. I'm ready to go.
Well, welcome back. And for people who don't remember, what do you do?
So I'm a graduate student. I'm at Penn State University, and I am studying tidal tails, so emerging galaxies. And so I'm looking for star clusters in those tidal tails.
Fantastic. All right. Well, thanks for coming back. Phew. Um, from the other side of the planet now, and you really got to admire their heroism here. It's very early in the morning. I'm not sure why they signed up for this, but first we got Alan Versfeld. Alan.
Yes, hi. It's not that bad. We are astronomers. We're used to being up late at night, so I think.
That's right. Now, Alan, you are, people may know you as the urban astronomer. You've been blogging for a long time. You've been in our Carnival of Space, and I know we've linked to a lot of stuff from Universe Today. But why don't you let people know sort of who you are and what you do?
Yeah, well, I mean, from South Africa, like you said, amateur astronomer since as long as I can remember. I've been blogging on Urban Astronomer for about, it's 10 years now,
Yeah.
and podcasting for about 2. And looking forward to seeing
what's the name of your podcast. I mean, we're going to give you a chance to shamelessly self-promote what you do at the end of the show, but for people who want to hear your podcast.
It's the Urban Astronomer podcast.
Perfect. Right on. Okay, and then I apologize in advance, Nika. I'm going to, Nika Klimovic. Is that right?
It's okay.
No,
Klimovic.
It's wrong. Say it
No
properly
worries.
so then everyone can. Klimovic. Klimovic. All right.
But
yeah,
but you can just call me Nika. It's fine.
Right, but So who are you? What do you do?
So I think I'm presenting Europe here in this show. So I am from Europe in Frankfurt, and I'm organizing various events related to space in Frankfurt to build up a local space community. And I graduated from the University of Bath, which is in England. I did aerospace engineering, and my dissertation was on energy harvesting in space using pyroelectric materials. And now I'm here trying to make space more accessible and understandable for people.
Fantastic.
So happy to be here.
And this is great. So some of the new co-hosts this year, you're going to see their faces again and again over the course of this whole season, and the goal is to bring more science communicators to the fore, give them a chance to share science news with an audience, and give them more practice, but also for us to use the massive following of Weekly Space Hangout to try and help more people get their word out there. So thanks a lot, Nika. This is I'm looking forward to hearing what you have to say. All right, so let's move on to the interview portion for our researcher this week who's been waiting patiently. So we got Dr. Georgiana Kramer from the Planetary Science Institute. Georgiana, welcome to the Weekly Space Hangout.
Thank you very much. I'm really happy to be here.
I'm so happy that Cthulhu is watching over your shoulder here. This is absolutely perfect.
Yeah, this is cuddly Cthulhu.
Why sell for the lesser evil? So now, who are you and what do you do?
I am a professional lunatic. I study the moon. My training is in geology. I got my undergraduate degree.
Lunatic. I get it. Right? Lunar,
Yep,
lunatic.
Yep.
Right. Okay.
So I got my undergraduate degree from the University of Hawaii in in geology and geophysics, and then my PhD at Notre Dame in planetary geology.
And what are, we'd had a chat just like sort of before the episode started, and there's a couple of pieces of research that you have worked on. And I'm sure I know how this went, and Nancy can probably just confirm in the chat if this is how it works, is that we reported on, I think, both of your stories, or stories that you've worked on as it relates to the moon. And at some point in the show, we're like, oh, we should talk to some of the researchers who worked on that. And then, of course, Nancy just makes that happen. And here we are talking to one of the researchers. So you know how much water there is on the moon, probably.
Actually, I I do a really good job of not quantifying it.
Yeah.
I'm kind of actually opposed to methods of trying to quantify it because we just don't have enough information.
There's like some, but not none.
Yeah, there's some. There's probably something pretty useful in the polar regions, but the water that I particularly study is this. It's a surficial phenomenon that happens across the entire lunar surface, and it actually has a diurnal cycle where it sort of when it becomes like lunar dusk, the hydroxyl and or water will start to sort of stick to the surface, and maybe like a few microns depth or something, and then it will stay throughout the night, and then when the sun rises 2 weeks later, it'll start burning off at the equatorial regions, or between like maybe 30 degrees north and south.
Right.
But as you go to higher and higher latitudes, that burning off doesn't happen so much, and it sticks a little bit better. And then you go to the poles, and it's just staying all the time.
So, like, I know that, like, as the moon goes through its day-night cycle, you get this process where like this static electricity, this charge is sort of moving across the surface of the moon, right? And then dust is being lifted up as the temperature changes. And what would it be like if you were actually standing on the surface of the moon as sort of shifting from day to night? Would you be able to see any of these particles, or is it just like trace amounts that only a spacecraft can find?
One of the astronauts, I think it was Apollo 15, he actually did see it, and he was the first one to he drew a little picture and he wrote about it, and that's and it actually has yet to be really like confirmed, but it's plausible, certainly.
Wow. And so then, like, where is this water coming from?
Well, what he saw was actually that levitated dust.
Right.
The water is likely being is coming from the sun as hydrogen protons, and the lunar surface is covered in fractured minerals and glass and such, and a lot of them are silicates and oxides, and the most abundant element there is oxygen. So when you break the bonds, you get oxygens that are not completely satisfied, and so they're going to have a sort of net negative charge. And along comes these positively charged protons, and so they might feel each other and want to hang out a bit. There might be them hopping around, some going, inside a little bit, coming back out, maybe hopping to colder regions where they can stick a little bit better. So as far as we understand it, the hydroxyl and or water that we're seeing surficially might be a transient phenomenon.
That's fascinating. So you've got the solar wind impact the protons coming from the solar wind, the hydrogen impacting the moon, turning into water briefly, and then
kind of hanging out with the oxygen.
The oxygen, and then dissipating because it's also being blasted by the solar wind. But near the poles, you think that maybe it can remain a little bit longer.
Yeah, so these the solar wind, these protons actually carry just enough energy to break some bonds actually, but also micrometeorites that come and impact will break bonds, and there's a lot of those happening. So there could be oxygens that get liberated, and they hang out with the hydrogen, and they might hop along towards the colder regions. I mean, they'll hop along, of course, chaotically, randomly, but the ones that keep going to colder and colder regions will find their way to the poles, maybe. And this is a theory about migration, how the one way, at least, that the lunar ice that's in the permanently shattered regions might have gotten there. One way.
And one of the problems, of course, all eyes are on how can we find deposits of water on the surface of the moon to support our long-term exploration plans. How hard would this water be to get at?
It could be somewhat difficult, but it's certainly I would hedge my bets towards at least some of this water for at least some preliminary space exploration is probably accessible. And the big question now is how deep and how dirty is the water. So meaning like how much of the lunar soil is actually mixed in with it. These quantification of that is not realistic yet. But if we get some landers over near the polar regions, then we can actually start getting some real numbers
and so
answers.
Are those like the questions that you would like to have answered next? Is just how much, how deep, how, is it cleanable?
Yes, right.
Right. Does it give like some kind of, I think if this has been streaming for a long time and it's been building up layer after layer for long periods of time and getting churned up with micrometeorite impacts and dust falling on top of it, does it give you some way to see the history of the sun, the moon, other parts of the solar system?
Yeah, absolutely. But also, probably some of the water that's sequestered in the polar regions probably comes from comets too. Even if the comets don't necessarily hit in the polar regions, there is a release of water, and that water again can do the same sort of hopping migration towards the polar regions, molecule by molecule. So that can give us some information about comets too in history.
Now, another piece of research that you work on is the lunar swirls, and these are amazing. I'm going to post some pictures so people can see. You won't see, but you're going to have to, work from memory.
Okay.
So, but what are these lunar swirls? How would you describe them?
So they are high albedo, meaning they're bright. They're always bright. They look bright no matter what the sun angle is. They look bright, sort of like fresh ejector rays. They usually have a curvilinear feature, which is why they're called swirls. They have, every single swirl is associated with a magnetic anomaly on the moon. The moon doesn't have a global magnetic field, but it does have these like just areas, isolated sort of areas where there is a high magnetic field, in some places even higher than the Earth's global magnetic field, or in several places actually. Although I do have to say that not every magnetic anomaly has a swirl, that's one of the mysteries still remaining. But what else about them? They so not only does these bright surfaces look bright, they also look immature. Let me get some water in me.
I'm just posting some pictures here where you can see the shapes of these lunar swirls, and they really look like wrinkles on the surface of the moon, like I don't know, like fresh, much lighter color material has been sort of dabbed on the surface of the moon in weird swirly shapes.
Yeah. Yeah, so again, in addition to them being bright, they look like they're fresh. So there's ways that we can, using spectral data, using data that goes, the visible and into the infrared, we can find out, we can make an estimate of how mature a surface is. And bright ejecta rays look fresh. And the swirls are some of the freshest looking features. They are comparable to like very somewhat recent impact craters, like very recent impact craters.
And of course, the question is, what's causing them?
What's causing them? So there was two major theories. One of them was comet impact, meaning that they really were fresh. The other theory, the one that's actually just standing up to further scrutiny over the last few years, is that these magnetic anomalies are areas where the solar wind, as it comes in with its charged particles and such, it encounters this magnetic field. Probably an electric field is set up, and a voltage difference is set up, which is then pulling the protons in one way and the electrons in another way. But the electrons really can't do anything to the surface. But the protons, like I said before, they have just enough energy to actually break bonds. And so they can actually be they can be liberating iron from oxygen, for instance.
Right.
And you can be getting left behind with, like, the oxygens take off, maybe they hang out with some of the hydrogen, they go up north. And then you have left over this iron, which was a 2+, now is a 0 valence state. And you start getting these little blebs of little black iron. We call them nanophase or microphase iron. And they get trapped inside of the glassy parts around some of the soil. And it causes the soil to darken. That's normal space weathering process, that it causes the soil to darken. But where these swirls are, where these bright features are, these appear to be areas where space weathering is being retarded. It's being held off. It's being blocked. So it seems like the protons probably aren't making it so much. And so the only thing that is left to actually start darkening the surface would be micrometeorites.
So it's like a negative.
What do you mean?
Well, like the stuff that we're seeing is actually the parts that are being where this is all happening is the parts where this process is actually being blocked, and so you can actually see the underlying.
I kind of like to liken it to putting suntan lotion on your. Like if you just kind of put some swirly pattern on your arm and then went out and burnt your arm, you would have a lunar swirl.
The protected part would be the swirly part.
Right.
But it's really fascinating how, I mean, it's got these shapes, and they are, I mean, they really they look like the auroras. Like you can see these very kind of organic aurora looking shapes, but they're on the surface of the moon. But it takes a long time. Like it would take millions of years for these shapes to form, and they're following the magnetic field lines of something in the moon.
Probably, yeah, they're following the magnetic field lines of whatever is underneath the surface that is generating it. But I wouldn't say that they took millions of years to form. I would say it's more like they won't go away. I would say that they've probably been there for millions, billions maybe of years.
Yeah.
The Mare Marginis one, which is looks like there's a fresh impact crater, and it kind of looks like you got these like swirly, so you got lunar swirls emanating from it. This to me looks like, which that one actually would almost be a great argument. Oh, it must be a comet impact, but really it's that impact. It's Goddard A is the name of it. It spewed out all of this bright highland material, and it fell. And then the whole area started getting older and older, but where the magnetic anomaly was, it kept this particular shape.
That's
so it kind of looks halfway like ejecta and like swirl.
But the bottom line is more research is necessary. We need to send a mission. It has to land there. It has to sample, and we have to find out what's going on.
Yeah, I mean, and more than that, the lunar swirls are a great place to study space weathering phenomenon. It's a great place where, if you had a lander that wanted to go and sample material, you could have it go and land like right on the edge of a swirl, because some of these boundaries are pretty sharp.
Yeah.
It could land like on a swirl boundary, and it could grab some of the stuff that's dark and mature and grab some of the immature area. And so the immature part can be holding more of a history about the lunar surface that we might not be getting because of solar wind implantation.
Incredible. Well, we're reaching the end of our time with you. Before we go, where can people find out more about what you're working on?
I guess the Planetary Science Institute website, there's a page that has, a brief little like what I do and what I'm interested in. I have a couple of grants from NASA and through the Lunar Data Analysis Program, and you can actually go and find out which grants were funded. And there is a one-page abstract that explains the work that's being done, what we're going to do, and such like that. If you wanted to go and look that up. And
should we make a pitch for the female superheroes of science?
Oh yes, please, yes. The female superheroes of science. We are recruiting. We're a group of female scientists and engineers who like to be role models for young girls and young men too, and hopefully inspire them to get into science and engineering. Yeah. And I am the lunatic phenomenon.
Right. Larry Beckham in the chat was saying he's an amateur. He's wondering how to turn pro. So maybe that's a place to find out more information. Well, thank you so much for taking the time to chat with me today. I'm really glad that your weather held out.
Yeah, me too.
For the duration of the interview. Now I hope that the weather holds for you. It doesn't turn sour. Thank you so much for joining us on the Weekly Space Hangout. And when you do figure out exactly what's going on, please let us know.
Okay.
All right. Thanks a lot.
Thanks. Bye.
All right, let's move on to the regular portion of this episode. And Brian, why don't we start with you? Tell us about the most massive neutron star ever found.
The most massive neutron star ever found. So this is a neutron star that is, I think, about 4,600 light years away, and it is a pulsar. So to give some background, A pulsar is basically a neutron star which has a strong magnetic field. So there are beams of radio waves coming out from the magnetic poles. And as this neutron star rotates, it spins, and these beams swing around like a lighthouse. And some of them happen to be pointed in our direction. And when we have a magnetic pole that's pointed in our direction, every time it spins, it has this radio flash, and we see that as a pulsar. And this one is actually rotating really fast. It's about 350 times per second. So we're seeing 350 pulses per second. And for that reason, it's called a millisecond pulsar, because the time of rotation is in the order of milliseconds, this tiny fraction of a second. So it's a pretty, at first glance, looks like a pretty standard pulsar. But because it's rotating so quickly, we can actually measure the pulses very precisely. And that allows us to do some pretty interesting things, because if you can measure the pulses really precisely, because they're due to the rotation, they're not going to really change much. So anything that changes in the timing of the pulses is usually for something else. So it could be the motion of the pulsar itself. As it moves towards us or away from us, there'll be some Doppler effect. But this particular pulsar is in orbit with a white dwarf star. And so this thing is orbiting, the white dwarf and the pulsar are orbiting each other. So we can see that motion from the Doppler effect. But the orientation of the orbits are such that the white dwarf basically passes in front of our field of view with each orbit. Now, what's interesting about this is because if you think of an orbit of a binary star, it depends upon how far away they are, but it depends upon the two masses of these stars. And so if you know how long it takes for the orbit to complete, how long each orbit is, you know one of the things you need. And if you know the mass of one of those stars, then you know you can calculate what the mass of the other star is. So what's interesting with these radio pulses is there's a relativistic effect known as the Shapiro time delay. And basically what it means is that if you have, say, a star and you have light coming near that star, it can deflect the timing of the pulses that are coming through. So you have this neutron star that's spinning really fast, and it's doing its little pulses. When the white dwarf passes in front of it, it shifts the timing of the pulses that we see.
Thanks to its mass.
The amount, I'm sorry?
I was to say, thanks to its mass.
Thanks to its mass, exactly.
Right.
So the amount of shift is actually directly due to its mass. So we can then determine what the mass of the white dwarf is. So we know the mass of the white dwarf, we know the orbital period of these two, and so we can calculate the mass of the neutron star. Incredible. And it turns out that this neutron star is right at the edge of how big we think a neutron star could be. So if you're familiar with white dwarfs have an upper mass limit. Right. They're held together by electron pressure. And if you have too much weight, it collapses.
Right. That's how you get like a type 1a supernova.
That's exactly it.
Right.
So that is about 1.4 solar masses, and that's known as the Chandrasekhar limit. So for neutron stars, the same type of thing happens. It's held together by neutron pressure. And there has to be some limit where if it's too massive, it'll collapse into a black hole. Now, there is this equation that calculates out what the mass of a neutron star upper limit should be, but it's really, really complicated. And so you don't get a simple answer. You get, if you run the equations, you get, well, somewhere between 1.4 solar masses and 3 solar masses. So we're not right sure what that is. But when we've looked at a neutron star merger with gravitational waves, so two neutron stars merging, and we look at the gravitational waves, what we get is that it's probably closer to 2. So around 2.17 solar masses.
But so they don't know like the specific math, like with the white dwarfs with that 1.4, the Chandrasekhar limit, like he did math to figure out what is the most mass you can pack into a white dwarf star. Like they arrived at that number mathematically, right? But is there not a mathematical number that you arrive at with a neutron star?
There is, but it depends on certain factors. So the white dwarf limit, the Chandrasekhar limit, depends upon electrons. And electrons are elementary particles, so they don't have any internal structure to them. Neutrons are quarks. So there's quarks that make up neutrons, and how those quarks interact is something we still don't fully understand. So the what they call the equation of state is still a little fuzzy when you get really at that limit.
So would watching a neutron star collapse into a black hole tell us some fundamental piece of information about quarks?
If we could get good data on that.
Yeah.
So the gravitational wave measurements put it at about 2.17 solar masses, because that seemed to be right where the trigger point is. So this particular mass, when they calculated out the mass, what they got was their best calculation was 2.14 solar masses. And the range was between 205 and 2.24 solar masses. So it's right at that edge of that neutron star mass limit. And it could be a little bit higher. We can't rule out that it actually could be more than that. So this is not only just the most massive neutron star that we've ever observed, it could very well be kind of the most massive neutron star that we can observe.
Right. The most massive neutron star in the universe.
Right. But even if it isn't, one of the things that it really does is there were some calculations that said, no, the upper limit should be under 2. Because we don't find neutron stars that have a mass greater than 2, so that it actually should be on the lower end, not the higher end. But this one, the lower limit is 2.05. The lower limit is greater than 2. So we know now that neutron stars can have a mass greater than 2 solar masses, which helps constrain what that equation is.
So what happens if it gets a little more mass? Can it be feeding from a white dwarf the way a white dwarf will feed from a star?
It could be. This one doesn't appear to be.
Right.
But if it's really, really close, suppose a meteorite hits it and gives it too much mass.
Yeah.
And then it could collapse.
Into what?
It would collapse into a black hole because it would be over the limit. Another thing that's possible is this thing's rotating really quickly. Over time, that rotation is going to slow down. So it's possible that the rotation is actually letting it have a little bit more mass than it would otherwise.
That's crazy.
And then as it slows down over billions of years, it'll reach a point where it collapses because it can't hold itself out.
Now, the thought was, I've heard as well that there are in between objects, potentially in between a neutron star and a black hole, some more compressed state of quarks or whatever, but not
like a quark star.
A quark star, yeah, not fully compressed. So I guess if we could see something like this make that jump down to the next step, that would be incredible. Would it give off some kind of I don't know, blast of radiation that we could detect?
Well, if it depends on again the equation of state, but let's say the typical model for a quark star would be you have a neutron star that's about the size of a small city, and a quark star is a good 20 or 30% smaller than that. So if that were the case, if you had this neutron star spinning, slowing down, doing whatever, and it collapsed, and it still kind of looked like a neutron star, it still was a pulsar, but it was spinning much faster. And you saw that not just a tiny shift like we see with starquakes, but an actual huge shift, then that would be pretty strong evidence that quark stars exist.
Yeah. But it's just crazy to see, to imagine this neutron star just spinning, and it slows down its spinning to the point that it just disappears. That'd be amazing. Wonderful. All right, let's move on. Although I clearly, obviously, really excited about this. We could talk about this this all day. Alan, what do you got for us?
Yes. So I believe, as I understand, a long-standing question in astronomy has always been the age of Saturn's rings, and it seemed like that was settled last year towards the end of 2017. based on data from the Cassini mission during its grand finale. And what Cassini found when it measured the rings was that it is almost entirely ice, 95% ice, I think, and about 5% other stuff. So the reasoning was that if it was really old, it would have picked up a lot more of the the dust and rock and other gunk floating around the solar system, and it would be much dirtier than it is now. And I think they said they worked out that the age should be about tens of millions of years or so, or thereabouts. Yeah.
And won't be around for long. Like that in fact this stuff was constantly infalling into Saturn, and it's only going to last for another 50 million years or so, and then the rings will be gone.
Yeah. But now a Dr. Krida of I'm going to try and pronounce this because I don't speak French, the Observatoire de la Côte d'Azur, does that sound right?
That sounds about right.
They reckon that some of the assumptions behind that are not accurate. According to them, there is a mechanism in the rings where material is transported out, shuffles along towards either the inner or the outer edge, and either falls into Saturn or drifts off into space. And in that way, material falling in gets flushed out again. Now, presumably, because this wasn't clear to me from what I read on their press release, this would mean that the ice must be being replenished as well. And we know that Enceladus is putting a lot of water and is replenishing the E-ring. It's not clear to me whether this ice is then moving to the other rings or if there's a similar mechanism to replenish the rest. But according to their models, the rings could be stable in this way for billions of years. Now, they're not saying that it means that they are billions of years, it's that they could be.
Right.
So, that's just reopening the question again, so we can never be settled.
Right. Because if there's one question we can't have answered once and for all, it's how old are Saturn's rings? Yeah.
So the story, I was taught when I was an undergrad, is that Saturn's rings were created from some moon that fell into Saturn, got tidally ripped apart, and then the debris formed those rings. Is that still the current hypothesis? Is that still what we think is the cause of that?
The different rings are formed from different sources. So there's actually, as Alan mentioned, there's ring material that's coming from Enceladus, and it's potentially ring material that was created by a torn up moon. But the question is just how long did this happen, and how quickly is this material getting sucked into the rings or into the planet? And when Cassini did its final deep dive, right at the end of its mission, it made a bunch of really useful measurements that astronomers were then able to use to determine that in fact the rings are very young. They're being pulled in very quickly, and they're not going to be around for very long. And now clearly the fight is on. So what does this mean, Alan? What do we do now? Continue to fight?
I suppose so. I mean, this debate has been raging forever, right? When I was doing a bit of homework for this, I've got this old 1960s textbook that I love to read because the fundamentals never change. And they were pointing out that there was, at that point, the debate was either, was it, as you said just now, was it an asteroid or a moon that disintegrated when it fell within the Roche limits of Saturn? Or was it just material that never coalesced into a moon, again, because it was too close? And that was as close as they'd gotten at that point. But every time more data comes in, then it seems to refine it towards one or the other. Voyager showed us a lot. Voyager discovered the shepherd moons, which showed that, okay, well, the system is actually stable. It could last longer than a few thousands or 10,000 years, whatever it was before. Cassini comes along and says, well, here's a maximum age. And now these guys are saying, well, hold on, there's more to it than that. So I don't know. Let's see.
Yeah. That's funny. Nancy's noting that Morgan could have been on this week. This would have freaked him out. Morgan was a researcher working with Cassini, so the rings. He was quite pleased when we got to the point that the age of the rings had finally been worked out, and so I'm sure he's already. We'll ask him next time he comes on the show and see where he's at. All right, Nika, what have you got for us?
Hi. So I have air pollution from the wildfires. So the wildfires have been, like in Amazon, in South America and Africa, have been big headlines, international
this was a big
headlines over
story.
the past weeks. Yeah. And the thing about it is that it's not only a huge environmental tragedy in terms of lost forest and biodiversity, but it also affecting our climate and and the air quality. So the trees act as a sink for the carbon by absorbing and gathering the carbon dioxide, which is the main greenhouse gas, and so also helping to cool the planet. But devastated by the fires, forests release a lot of this carbon dioxide back into the atmosphere. So this particular article was on air pollution conducted by the Copernicus Sentinel mission using TROPUS instrument. And this instrument was or is tracking basically 6 or 7 various gases. And when you analyze the air pollution caused by fires, the most relevant are 3 of them. So it's carbon monoxide, I hope I will pronounce it right, formaldehyde, and aerosols. So the images that ESA made all show the increase in carbon monoxide between July and August following the fires. So the carbon monoxide is normally associated with traffic or burning of fossil fuels, but after the fires and the increase in the carbon monoxide was basically a drastic increase, and this gas actually is bad for humans because it reduces the amount of oxygen that is transported into bloodstreams. Another gas which was tracked and it was also increased is the formaldehyde. And there was a comparison of the amounts of this gas from the last year and this year, and there's a huge increase. And it's also an indicator that in both continents, Africa and South America, there were more fires this year. And this intermediate gas is actually short-lived in atmosphere, but it also reacts chemically and to become a source of this carbon monoxide that I was mentioning earlier. And another big thing is tracking of the smoke and aerosols after fires, because once breathed in, the small particles, it can cause cardiovascular conditions and lung cancer. Or lung problems actually, and aerosols also affecting climate by absorbing the incoming sunlight and by trapping the outcoming long-wave radiation, so it's warming the planet.
Right.
And as an example, the Brazil fires in August, the smoke from the Brazil fires was having the aerosol indicator 4, and 5 is the highest value. So in 19th of August, the day turned into night in São Paulo, basically.
Yeah.
And then with this big air pollution and the climate change as a major global topic, it is very important that the satellites tracking this the atmosphere, and so that also authorities can help to react on these incidents like the recent fires, and also by creating environmental policies.
It's pretty fascinating, like how much like now with the amount of Earth observation satellites that are up there, both from NASA and ESA, they're able to really keep a worldwide view. So, you know, this kind of environmental devastation has been happening for a long time, but we're now getting just really up to date. We can see with great precision how awful it is. Here
you can even send. Oh, sorry.
Oh, I was going to say, so here in British Columbia, we get wildfires every summer. This summer wasn't bad, but usually it's terrible, and yeah, the smoke is awful. The sun turns red in the middle of the day. Everything kind of takes on this reddish hue. It's terrible, and it's killing huge amounts of trees. And this has always been happening to some extent, but now you see all of these fires, you see the emissions leaving all of these areas. It's just in stark detail. And I think that's why, I mean, it was such a big news story over the summer, all of the burning that was happening. People were posting lots of pictures, but the satellites are really telling the story.
Yeah, they're telling the story, and you can actually even set up an alert for your area. There are already like tools also provided by NASA and ESA, and it's very interesting also to follow up that these fires, so a lot of these fires are actually happening always in the same areas over the years and years. So basically they tracking like for, 20 years already, and you could see that it's pretty much on the same areas. And another interesting thing was for me that I realized that many of these fires that were in Africa and in South America that were actually caused by people and intentionally. And that is, I think, the worst. And it was even discussed in other articles in NASA Earth observation website. They were showing how it is actually more intentional and not like because of the dry season or something.
Well, you've got these crops, you've got things like palm oil plantations that people are clearing land to do these palm oil plantations, and it's too expensive and too difficult to clear the land by cutting down the trees and using large heavy equipment. The cheapest way for them to clear a big chunk of land to plant a whole bunch of palm trees is to just burn it, and then boom, you've got nice cleared land. You've also your wildfires have gotten out of control, but you've got nice clear land that you can now plant your palm trees. And then, of course, a lot of the food that we have has palm oil in it. So, it's possible that we're helping to contribute for the demand of palm oil. But I mean, I know watching this unfold, it was like on the one hand, you're just sort of watching with horror at the amount of wildfires and all these different gases that are being released. And then the other side, you're just like, wow, look at what satellites are able to see. Like there is now no way to hide. There's no way to do this kind of thing and not at least for people to know that it's happening now, which is helpful.
Yeah, amazing. And I lost one picture, but it was just the amount or the scale of these fires is just crazy. They put one of these fires on like the satellite picture of these fires in Amazon to territory of the UK, and it was like basically 1-to-1 size. So if you just imagine, it's the size of the country almost. So, and you could see it by using this data from satellites. So it's just amazing, and maybe it raises more awareness on this topic.
Fantastic and terrifying. Michael.
All right, so less depressing than our Earth being burned is that we have potentially discovered another interstellar object. So we had Oumuamua last year, and now we have Comet C 2019 Q4, which was discovered on August 30th and is believed to have come from outside of our solar system. So this was actually discovered by an amateur astronomer. He built his own about 0.6 meter telescope. He's found a bunch of comets, and this is the first one that's been found that is interstellar, not from our solar system. And so one of the questions you can ask is, how do we actually know that this is not just a regular comet that's, in the Oort cloud, And this is actually moving at a very high velocity. So it's at 41 kilometers a second right now.
Wow.
And it's still like around Neptune's orbit. And so it's still speeding up. It's still getting closer to the sun. It's going to go even faster, top around 45 kilometers a second. And it's on a hyperbolic orbit, which means that it is not bound to the sun. So this comet is just going to kind of come in, speed by, pass by the sun, and then get tossed back out of our solar system and go back on its path.
Do you know how close it's going to get to us? Like you say, it's out right now, out by the orbit of Neptune. So we've got some time to prepare for when it gets a little bit closer.
I don't actually know like how physically close it's going to come to the Earth. It is going to get close enough that it's going to increase its brightness a lot. So it's going to peak at about 15 magnitude in December to January.
Right.
So if you have like a 12-inch telescope, you can probably check it out yourself at night.
But it's going to be moving fast, so you're going to need really updated star charts.
Yeah, it is.
Alan, do you think you could take a crack at it? Have you got the right gear for that?
No, I didn't. 8-inch scope, but
you need a bigger
maybe
telescope.
A long exposure photo would take it. Yeah.
So, Michael, I mean, whenever we heard about Oumuamua, the goal is like, how can we get close enough to learn more information? Now we've got more warning with Oumuamua. We saw it when it was on its way out. So how can we find out more about it?
Well, we kind of dropped the ball on this one. If we had known about this last July 2018, some people actually did some research on this, and you could have launched a Falcon Heavy in July 2018 to meet it in October 2019. Obviously, we didn't know about it then. So the next thing we can do, if you want to like actually go to the comet, there is another launch window in 2030 that would require the use of an SLS. The Space Launch System, and you could launch a CubeSat on that, and you could beat it in 2045.
So you could take an SLS, you could take a $1.5 billion spacecraft. You could put a satellite on top of it that you could pick up with your hands, and all that SLS would be used to accelerate your tiny little CubeSat on a velocity that would allow it to meet with this interstellar comet in 2045.
That's money
worth
well spent,
it.
I think, right?
Done. Sold. Have you heard about the idea of ESA's proposing their Comet Interceptor probe? Have you heard about this?
I had heard of it.
Yeah. So they're going to launch the plan right now is they're going to launch a spacecraft with the Aerial Space Telescope, which they're launching in 2028. And this is going to be a tiny, probably in the CubeSat department. It's going to loiter at Sun, Earth, L2, and then wait, for a target like this. And then when the right moment comes in, it'll crank up its engines and try to make an interception, and maybe even like an impactor on an interplanetary thing. What could we learn? I mean, if we actually could get more information, what could we learn from an interstellar object?
So the composition, I think, is the biggest one. We want to see what is it actually made out of. So right now, we actually do have quick spectra that was taken of this comet. It's an active comet, so it's got a coma. It's nice and fuzzy. And right now, it looks kind of boring. It actually looks like a solar comet. So it looks like just a regular comet within our solar neighborhood. So if you can get more spectra, so right now we just have a spectra that's taken like on the red end, we can get one that's taken more on the blue end and figure out what it's made out of, what kind of molecules it has, figure out, what other kind of solar system did it come from? Is it like the sun? Is it completely different? So just trying to determine like what this thing is actually made out of. Is it actually just an alien solar sail? We got to get close to it to find out, right?
Oh, don't even bring that up. That was the cause of so much controversy in seasons gone by. But that's yeah. I mean, at least we know it's a comet. Like that was the question with Oumuamua. Is it a comet? Is it an asteroid?
Right, and this is kind of like if you're going to look for a interstellar object, this is like the stereotypical one that you would want to find, a nice bright comet, nothing confusing like we had last year. This is plain and simple, a nice comet that we can relate to what is in our own solar system.
That's amazing. Well, before we go, we're sort of running out of time, so I'm going to share a couple of pictures, and I will share this with my co-host. Hopefully they can see me now. All right. So the first picture here is a photograph of Jupiter with a transit, with an eclipse of Io passing over it. And this was a picture taken by NASA's Juno spacecraft, and it was processed by friend of the show, Kevin Gill. And this is Io. It's incredible. Like, what a picture.
That's stunning.
It's just gone. Yeah, it's just gone, taken off like wildfire on the internet. But we see them. We see those transits of the planets. We see of the moons of Jupiter, and we see those shadows in our telescopes. But to see it from this perspective, I've never seen anything like it. And you first see this and you go, oh, it's fake, and you're like, oh, Kevin Gill worked on it. It's real. So
it's interesting to compare to those eclipse photos you see on Earth from the ISS, where you see the moon shadow, but that's got a much fuzzier edge, a much wider penumbra than this one.
Yeah, just stunning, just amazing. So that's one of the best pictures I've seen in a long time. And then I got one other thing that I just want to show everybody, and this is a time lapse that came from a astrophotographer named Eric Brummel, and let me see if I can get this to work. Okay, here we go. All right. So he took a time lapse. Oh, come on, little internet. All right, here we go. Okay, so he took a time lapse of the Milky Way, and we've seen this many times before, but what he did was he locked his picture on the Milky Way and let the Earth turn underneath. And so you can see the rotation of the Earth as it compares to the Milky Way, which is just an absolutely amazing picture again. I really, really enjoyed this, and we had a big long interview with him on Universe Today. But
why has nobody done this before?
It's been done before.
Great.
Yeah, it's been done before. I've seen this a couple of times. So,
okay.
But Eric has done one of the nicest versions of this. But you just, like, this is your planet that you're living on, and it is turning, and there's the Milky Way. And so you just get this sense of what's going on. So I really, I just wanted to share these two pictures because we don't have a lot of time. No time for actual news, just pretty pictures. All right. So Alan, you're on my screen right now. So why don't you tell people where people can find out more about what you're working on?
Okay, well, easiest place is just to follow me on Twitter. Although if you don't like politics, maybe just stick to the website. That's @uastronomer. Otherwise, you can see what I'm doing, both the blogging and the podcasting, at the website address, which is urban-astronomer.com.
Thank you so much. Michael, where do people find out more?
So I realized I need to get Twitter, man. This is like, I'm kind of old and holding out on this.
Yeah.
I need to get my own Twitter right now. I just got a website, Penn State website, so sites.psc.edu/mroderick. You can see the research I'm doing on there.
That's
next time I'll have my Twitter up.
There you go. That's how you turn pro. Now the pro move is to not actually read it, but just make sure you have it.
Yeah.
All right, Nika, where can people find out more?
I have the same issue as Michael. I think I need a Twitter account. I feel like I'm not sharing enough.
Yeah.
No,
you don't need to share. You just need to have a place that people can find out who you are and what you do, and be able to reach out and invite you to come on their podcasts and talk about space news and aerospace.
Yeah, basically, yeah, it's a good idea. But currently, the only way to find what I'm doing is on Meetup. If you've heard about it, it's and I have 2 groups there. and we do amazing events.
So can you just mention this briefly? So what's the next event that you're working on?
Okay, so basically the next one will be in October, and I have two speakers, and they are both having like a startups, spin-offs of space technologies. One is working on maritime autonomous navigation, and the other one, they have an app that analyzes the quality of the soil of your fields. And basically they are both like German startups, and it's very interesting to hear how they use the technology, how they get the data, because the data is available and it's for free to everybody. So it's basically how you use it, just take it and make your own thing.
Very cool.
So
and is it it's in Germany where people can go and actually attend?
It's near Frankfurt in Darmstadt.
Okay.
And in Darmstadt, you have also European Space Operating Center.
Yes.
So that's why it's a kind of space hub here.
That's cool.
So yeah, that's the next one.
And Brian.
And the one after. Oh, sorry.
Oh,
it's okay.
Brian. Where do people find out more?
Find me on Twitter at Brian Koberlein. You can find me on my blogging is on my website, which is briankoberlein.com. And if you're interested in Big Science, the hopeful TV show, you can go to bigscience.ca because it's Canadian.
Perfect. Fantastic. So this week we just posted a video all about plans to build a base on Phobos on my on the Universe Today YouTube channel. So if you're interested, you're like, why go all the way to Mars? It's dangerous. Just go to the moons of Phobos first. It's kind of like a base camp before you attempt a mountain, but in reverse. Check it out. It's a fun video. All right, I'm going to bring everybody back. Let's see if we got everybody. We'll get on the screen right now. Well, hey, thanks everyone for joining us for this week's episode of the Weekly Space Hangout. A big thanks, of course, to all of our co-hosts. You guys did a great job. Can't wait to have you. I'm not sure you'll be back on in various times. I know Nancy is controlling the schedule, so I know it's going to be a sort of a rolling combination of people for the next while. But really appreciate you bringing the news and helping me share all this information. Thanks for a special guest. Thanks to all of our moderators working in the chat, everyone watching. We will see you all next week. Bye-bye. So we all wave. Bye-bye. All right, thanks everybody.
See you all.
Let me just shut this down.